Okay, so we're looking at the ideal gas law today. Here's the equation for the ideal gas law. The important thing about the ideal gas law is that it's used for only one set of conditions. So it's just one state that the gas is in where you know three of these four variables, whether it's the pressure, the volume, the number of moles, or the temperature. R is a constant. You can see there's a whole bunch of different constants that are available here. The one here with the arrow pointing to it is probably the most convenient one. It's got pressure in kilopascals, the volumes in liters, the temperature is in Kelvin, as it is with all the gas laws, and then we have the number of moles. So just part of where we got this constant from is just one fact that is true about all these gases in this table. If you look at it, it doesn't matter which gas it is or what its molar mass is based on the periodic table. The number of liters that this gas will occupy at STP, which is 0 degrees Celsius and 1 atmosphere pressure, is almost all exactly the same at about 22.4 liters. And that's where we actually get the idea that we can use this equation for any of the gases that we're interested in. Okay, so, and the neat thing is, not only does it not matter how heavy or what the molar mass is of each of these gases, or it doesn't matter how it's composed. So we got the helium atom, it's just one atom, okay? The argon atom, it is a much larger one. The hydrogen gas is actually two atoms as molecules, okay? Nitrogen, a little bit bigger, two atoms again. Okay, attached oxygen, a little bit bigger there, okay? And then carbon dioxide, again, a little bit bigger as well. So it doesn't matter which gas we're dealing with, number of atoms in the molecule or its mass, they will all occupy the same volume, okay, at STP. So if we use this formula, we can, and we're given certain conditions for any of the gases, we can figure out the number of moles or any of the other measurements that we have for the gas. So in this example, it states that it's 2.5 liters of container is filled with sulfur dioxide gas. And if you remember, sulfur dioxide is one sulfur and two oxygens. At a pressure of 120 kilopascals and a temperature of 26 degrees Celsius, we're looking to calculate the mass of the sulfur dioxide in that container. Okay. Well, we first of all identify all the information that we have in the problem. We have 2.5 liters, and that is a volume. Okay. We got a pressure of 120 kilopascals. And then also we have a temperature of 26 degrees Celsius. So before we get going here, we're going to make sure we change it right to Kelvin. So adding 26 and 273, 299 Kelvin. Okay? And then, now the problem is asking for the mass. So in this formula, we don't have a variable for mass. But we do have the pressure, we do have the volume, we do have the temperature, we always have the constant. So the only thing that's left here is that we can calculate the number of moles. And if you remember, the most important idea of this entire course is that if we're trying to find out the moles of any sample, we can figure that out either with formulas like this or the mass of the sample. So that's what's going to allow us to figure out the mass of the sulfur dioxide. So once we find out the moles, we'll use this formula, moles times molar mass, to calculate the mass of the sulfur dioxide. Okay, so we'll just plug in all our variables that we have. Pressure, 120 kilopascals. Volume, 2.50 liters. Number of moles, this is what we're looking for. We're going to use the constant that's given there, 8.3145 liters, kilopascals per Kelvin mole. Okay, and then we're going to multiply it by the temperature, which is at 299 Kelvin. Okay, and as you can see, all the units match. Okay, we've got our kilopascals, they're going to cancel out. We've got our liters, they're going to cancel out. We have our our Kelvin, they're going to cancel out. So we're going to rearrange this equation. That's all multiplication, so the opposite is division. 8.3145 divided by 290, and that's going to give us the number of moles, and it's going to give us moles based on that constant there. Okay, so we're going to divide our final values, and we get a value of 0.1207 moles. Okay. Now again, as I had mentioned, they want the mass of the sample. We'll find out the molar mass, 1 sulfur and 2 oxygens. Sulfur is 32.06, oxygen 16, and give us 64.06 grams per mole. And when we multiply the moles by the molar mass, we get the mass of the sample. 7.73 grams.